morning, good afternoon, and good evening, everyone. Welcome to this tutorial where we will today learn about Hadoop architecture. Now, in previous sessions, we discussed working of HDFS and how HDFS is used for storing data across slave machines, or what we call as data nodes. So let's learn a little bit more about Hadoop and its architecture. Now, we have already discussed and learned about how big data evolved back in the days when there was no internet. Data was less and most probably structured, although organizations have always given a lot of importance to data, right? However, this data was easily stored on a central server storage, or we could say all the data was stored at one place. And as I mentioned earlier also, that the chances of 100% data being online was less. In fact, you would have 20 or 30% of data which would be stored, which would be online, and rest of the data would be archived. Now, as big data came into place, the data which is huge, data which is getting generated with a lot of speed, data which is having a lot of variety, right? And this all came in with the boom of internet. We not only had data in volume and velocity, but we also had variety of data. And we are having variety of data which is getting stored, which organizations are interested in. Now, this variety brings in different structure of data. So we could have a semi-structured data, unstructured data, or even your structured data. And as discussed earlier, organizations are interested in getting insights from this data. Now, this is where data becomes more important. And since organizations are interested in all of it, because then they can be more precise in their analysis, then they can be more good in knowing their customers, understanding the dynamism of business. Organizations would be interested in a solution which allows them to handle this big data. Now, at that point of time, or I would say in past, central storage was good enough. But then storing huge volumes of data, which is getting generated with a lot of speed and having a lot of variety embedded in itself, it's no more a feasible solution to have all the data stored on a single server. It's not efficient. So there was a need for distributed storage machines where data could be stored and processed parallelly in a distributed fashion. This is where solutions such as Hadoop came into existence. Now, if organizations could tap into all the data being online by having it stored across multiple machines, by having it processed across multiple machines, then they could really benefit from this so-called big data, which could be used for various use cases. And this is where big data technologies such as Hadoop being a framework came into existence as a solution. Now, what is Hadoop? What are the components of Hadoop? What is SDFS? And what is SDFS architecture? This becomes very important for anyone to work on big data. Now, there are other programming models. One of them is Hadoop MapReduce, and basically Yarn, which takes care of resource allocation. So we will learn about all of these from here. Now, when we speak about Hadoop, it's a framework. It allows you to store large volumes of data on several nodes or several machines or several node machines, as you would call it. So Hadoop is not a software. It is not just a technology. It's a framework. So it not only allows to store huge amount of data, or I would say big data, which has different characteristics, it also helps in processing the data in a parallel manner. When we talk about components of Hadoop, so basically there are two main layers. You have HDFS, which is the storage layer, which allows to store data across machines in their disks. We have Yarn, which is the processing layer. So when we talk about data getting stored across machines, then we need to have a mechanism that we can process the data which is stored across the machines. And for this processing layer called Yarn, which basically takes care of resource management across the cluster. And then you have various processing frameworks. So if you would be working on structured data, you could use something like Hive and Impala. If you're working on streaming data, you could be using Kafka or Spark. If you were working on batch-based processing or batch-based data, then you could be going for MapReduce. So MapReduce is the oldest and the most mature programming model, which is for processing data in a distributed fashion. And these are three important components of Hadoop. Now, when we talk about Hadoop ecosystem, then there are different components. Like you have Hive, you have Flume, you have Scoop, you have Kafka, you have Spark, and many more, right? But the main three components you could say is the storage layer, that is HDFS, the processing layer, that is Yarn, and MapReduce being the programming model. So what is SDFS? We have learned on SDFS earlier also. So it is a storage layer of Hadoop that stores data in multiple data servers or multiple slave machines, right? So data is divided in multiple blocks. So we have learned about this, that whenever a file is to be stored, that file will be broken down into blocks based on the size of the file. So when we talk about SDFS, the default block size is 128 MB from Hadoop version 2 onwards, which basically means any data you are storing, if that is up to 128 MB, that will be stored in one block. So block is just a logical entity to take your data to the disks of the slave machines where the data will actually be stored. And anything or any file which is above 128 MB will be split into blocks, where blocks will contain the data which is above 128 MB. So for example, if I have 129 MB of file, then I would have two blocks. One block containing 128 MB data and other block containing only 1 MB data. However, remember, when the block goes and gets stored on the disks, it will only occupy the space for the data it contains, which basically means that if I'm storing a file of 129 MB on SDFS, it will use 129 MB on the disk with the replication. So when we talk about data getting stored on SDFS, data is divided in multiple blocks, and these blocks are randomly distributed and stored across the slave machines, which we could say storing the data over multiple nodes of the cluster. Now, we have also discussed about the roles or the processes or what you call as components for every service. So for example, HDFS as a service, if it is part of your cluster, obviously it has to be part of your cluster, that's the main service, has mainly three main components or three main roles or three main processes, whatever you would call them. Those are your name node, which is the master process. So if a node has name node running, I would call that as a master node, which would contain metadata in its RAM and in its disk. You have secondary name node. Now don't go by the name. Secondary name node does not mean it is a second name node. Secondary name node is moreover a checkpointing node. It is a node which would have a copy of name node's metadata on disk. However, it is not a hot standby, which basically means that if your name node fails, your secondary name node will automatically not become the name node. However, since it has a copy of name node's metadata in disk, it can be used to bring up a new name node. Or you could even start name node process on the machine where secondary name node was running, and then secondary name node could be running somewhere else. And you have slave nodes, that is your data nodes, which contain the actual data in the form of blocks. So this is how your SDFS works. So if I would have to say that SDFS has to be efficient, it is ready for storage, it is ready for offering the data for processing, then these three processes, as we call in Apache Hadoop, or these three roles, as we call in Cloudera, or these three components, as we call in Hortonworks, have to be functioning properly. When we talk about blocks, as I discussed earlier, your SDFS divides larger data into different blocks. Now, even if I had a 1 kilobyte file to be stored on SDFS, it would still utilize a block of 128 MB. But remember, when the block goes to the disk, it will only occupy 1 kilobyte of space. So SDFS divides large data into different blocks, and these blocks are randomly distributed across nodes. Now, this is how it would look if you would store a 542 MB file where we have 5 blocks, 4 blocks containing 128 MB data, and 1 block having data of 30 MB. Now, when we talk about replication, the first rule of replication is that you would never have identical blocks sitting on the same data node. So if I have a block A on data node 1, I would never have a replica of block A on data node 1. So it would obviously be on some other machine. And replication has a second rule when it comes to rack-aware cluster. So what are racks? Racks are like your bookshelves. In case of a bookshelf, shelf. On every shelf, you would have multiple books. In case of a rack, you have multiple levels. On each of these levels, you would have a machine or a node. Now, if a cluster is rack aware, that is, you have not only placed your machines in the rack, but the cluster manager, that is name node, is also aware that there are racks which are storing these nodes. Then replication has a second rule, and the rule is you will never have all the replicas on the same rack. Even if your replicas were placed on different data nodes, for example, I have block A here, I would say my block A could be residing on data node 1, data node 2, and data node 3. But that is true when you are not in a rack-based setup. If you're in a rack-based setup, out of 3 replicas, assuming our replication factor is 3, at least one replica will be placed on a node on a different rack. So that gives you more fault tolerance. Now somebody could say, can I have 3 blocks placed on 3 different racks on 3 different data nodes? And yes, it is possible. However, to take care of your redundancy, you're increasing your bandwidth requirement, which might not be required. Also, if 2 replicas are placed on a rack on 2 different data nodes, they being co-located can benefit your performance. So the rule of replication is, the first rule, you will never have identical replicas on the same node, and the second rule is, you will never have all the replicas placed on the same rack, even if they are on different data nodes. Now that's a rule of replication followed in a rack-aware cluster, or in a cluster which is made aware that machines are placed in rack. Now there can be different topologies here. When you talk about rack awareness, there can be different topologies. A setup could have one rack which would have all the machines which have master processes. For example, I could have a name node and then a resource manager and then a edge-based master and something else critical, and all the master processes related nodes would be in one rack, and my other racks would only have slave processes related nodes. That is one kind of setup. The other kind of setup could be, on every rack you would have at the most one master process related node, and rest of the nodes would have slave processes. So that depends on the organization, that depends on the hardware setup, that depends on the management decision in deciding what kind of setup is preferred, right? Based on that, it can be decided if you would have dedicated bandwidth, dedicated power supply, cooling for a particular rack because it has master processes related nodes, or you would have a same or similar kind of setup for all the racks. So here we see that we have different blocks, and they are placed in such a way that you will never have all the 3 replicas existing on the same rack. So this is how your rack awareness works in terms of your replication of blocks. Now in this case, even if you have one block or one node on a particular rack missing, we would still have 2 copies of the blocks existing. Now this is also fine if you had placed blocks in 3 different nodes and 3 different replicas. However, it is preferred to have a block placed in such a way that you will only have one replica existing on a different rack, and other 2 replicas will be placed on the same rack but on 2 different machines. Now we have already discussed about SDFS architecture and how it works, so this is the overall picture in how it looks. So you basically have the master, which is your name node, and then you have your secondary name node, which is more of a checkpointing node. Always remember, secondary name node is not a hot standby. In fact, to tackle that problem, that if your master machine fails and you would want to have immediately a different machine to take care of your cluster, we have features of Hadoop such as high availability and federation, but we'll learn about them later. So if you look at this overall architecture here, you have name node, which is the master node, or you can say node which has the master process running, and this name node will have metadata in RAM and metadata in disk. I'll explain in detail about metadata in RAM and metadata in disk. So however, your name node has metadata in RAM and disk both. Secondary name node, which has a copy of name node's metadata, would only have a copy of metadata in disk. So whatever name node has as metadata in its disk, secondary name node keeps doing the checkpointing and has a copy of that. Name node in RAM is having more of operational information, such as what are the files are broken down into which blocks, the blocks are residing on which data nodes, and what are the file permissions. Data nodes, which are basically your slave machines, are the machines where the data is actually getting stored on the disk. Now this is how it would look when we talk about name node. So if a file was stored on HDFS, its information will be there in the metadata in disk in the form of edit log and fsimage. I'll explain about that again. And we will also have metadata in RAM, which has information of what is the file is broken down into which blocks, the blocks are residing on which data nodes, and what are the file permissions. Now in a non-high availability cluster, there can be only one name node. In a high availability cluster, there is a possibility of having 2 name nodes. However, in high availability, you would not have the secondary name node. Secondary name node is only allowed when you have one single name node, and secondary name node does the checkpointing. In a highly available cluster, we would have 2 name nodes, one is active, one is standby, and basically we don't need a secondary name node for doing the checkpointing. Now taking it further, when we talk about reading your data or writing your data to your Hadoop cluster, that is where your name node is already aware of where the data resides. Now let's talk about that, which talks about data node storing the information and how a read and write happens, how checkpointing happens. So we have discussed about this when we talk about SDFS architecture. Let's also understand a little bit more on what name node does, how does it store the metadata in disk, metadata in RAM, and what happens when a file is getting stored or is being read from the cluster. Now as we know, name node is the master. It basically helps to execute file system namespace operations such as opening, closing, renaming files and directories. Even when you delete files and directories, in all of those operations, name node is involved. And your data node is basically storing the blocks in the disk. Right now, when we discuss about SDFS working, we also discussed that every 3 seconds, as soon as your cluster is up, every 3 seconds, data node send their heartbeat to name node. And name node is already aware of which data nodes are available in the cluster, and basically it registers this information in its RAM. So that's the first metadata which name node has. Once the data starts getting written to HDFS and data nodes start having the blocks, data nodes will also keep sending block report to name node every 10 seconds. And that's how name node will have more information in its RAM. So here it only had information of what data nodes are available, but then it will also have information of what are the files which are written to HDFS. Those files are split in which blocks, those blocks are residing on which data nodes, and what are the file permissions. So this metadata in RAM is dynamically built every time the cluster comes up. So if we have a Hadoop cluster, it was shut down and it comes up again, name node will be waiting for data nodes to send their heartbeat and also the block report information, and name node will store this information in its RAM. And that is what we mean by metadata in RAM. When you talk about metadata in disk, this is created right in the beginning when formatting is done. So let's understand that how name node stores this metadata, which is in its disk and in its RAM. And this metadata is used when a client would want to do some operations on SDFS, when a client would want to read some data, when a client would want to write some data. It is always name node's metadata in RAM which is checked for further working on SDFS. Now we know that data node stores and maintains these data blocks, and data node will be responsible to not only store the blocks but also retrieve the blocks when name node passes an instruction or when name node is asking for those blocks. Now before we get into understanding how this reading happens, when a client talks to name node sends the response, and that's how client knows which data nodes are available to store the data. Let's also understand about this metadata part, and also one more important aspect, that is checkpointing. Now to understand that, as I discussed earlier, that is your SDFS which is ready for storing your data. So the first thing, whichever distribution of Hadoop you're using, say Apache Hadoop or Cloudera, you would basically have all the parcels or packages downloaded. You would have the configs which are edited, and once the configuration files are edited, then there is the most important thing, that is formatting of HDFS. Only once this is done, your cluster can be started. So I can say formatting of SDFS is done only once, and it has to be done once, and then start the cluster. Now whether the cluster is being started by scripts manually using, as we see in Apache Hadoop, or whether the cluster management solution like Cloudera etc. Or Ambari in case of water nodes does that for you. The cluster would be started. However, when the cluster is started, the first process which will come up is your name node. And for your name node to come up, it needs the initial metadata. So what happens here? Let's assume that at 10 a.m. a format command was given. So there is a command called HDFS name node format. Obviously, this command is given on the node where name node is supposed to run, and this formatting command would create the initial metadata. So for example, if I say that this is my metadata path, which we had specified when we did editing of config files. So when we do the editing of config files, either in a manual way or when Cloudera does that for you, there would be paths specified where name node would store its metadata on disk, where data nodes would store their data in the form of blocks, and so on. So let's assume that this is the path which was mentioned where name node can store its metadata on disk. So once the formatting is done, the initial metadata which gets created here would have a FS image, which is the file system image, like this, and then you would have a transaction ID file, and you would have a version file which gets created, and this version file actually has the initial identifiers, that is namespace ID, block pool ID, and your cluster ID. So these are the identifiers which are created and stored in this version file in the metadata path which was specified. So we can say this is my metadata path on name node's disk. Now as of now we have not started the cluster, only formatting was done, and this formatting creates the initial metadata. Now let's assume that at 10:01 you would start your cluster, or your cluster was started. Now as soon as your cluster starts, within 3 seconds your data nodes are sending their heartbeat to name node. So they are already registering themselves with the name node, and at this point of time what happens is your name node passes on these identifiers to the data node. So basically your data nodes would also have a version file which would have these identifiers, and this is one of the reasons I mentioned that you will never ever do a formatting again, because if you do a formatting again, it will change the identifiers and the metadata. In fact, it will reset it to the initial stage in the metadata path, but that automatically will not be updated to the data nodes. So then data nodes will not be able to contact name node because name node has a new metadata. So we will never ever do a formatting again unless and until you want to really set up a new cluster. Now coming back, name node gives its identifiers, that is version file contents, to data nodes, and data nodes will also have the identifiers which data nodes can use whenever they talk to name node to identify themselves. Now at this part of time, I can say that we can talk about metadata in disk and we can talk about metadata in RAM. So at this part of time, when we talk about metadata in disk, we would just have the same entries what we saw earlier. Now the cluster has started. We will have metadata in disk which has FS image as of 10, transaction ID, version file, but you will also have something called as edits in progress, and this is like a transaction log. This is something where any changes done to the SDFS will be stored from 10:01 onwards till the next checkpointing happens, which I'll explain later. You will have all the changes getting recorded in edits in progress. And at this part of time, the metadata in RAM is just about data node info, that is data node sending their heartbeat and registering with the name node. So name node is already aware of which data nodes are available. Now let's say at 10:02 a.m. you create a directory on HDFS. Now directory is just an empty structure, it does not have some data, right? So there will be no blocks. You're just creating a directory on HDFS. Now at this part of time, if we again talk about metadata in disk and metadata in RAM, we will just see that this timestamp will change, which notifies that there is a change which is recorded in edits in progress. And at this part of time, metadata in RAM is still having information only about data nodes, which data nodes are sending heartbeat every 3 seconds. Now at 10:03 a.m. let's create a file. We can call that file of 256 MB in directory on HDFS. Now this file basically means that now blocks will be created. So your file will be split in blocks, and those blocks will be randomly distributed across your data nodes. So at this point of time, I could say that my metadata in disk would have a new change recorded in edits in progress as per when you did the write. And once the blocks are written and data nodes send the block report to name node, metadata in RAM will now also have information about file. The files are split in which blocks, the blocks are residing on which data nodes, and then your file permissions. So my metadata in RAM is getting built and my metadata in disk is registering the changes. And this keeps happening every time you write data to HDFS. Metadata in RAM is having newer information, metadata in disk is having the changes recorded in edits in progress. Now let's say at 10:05 we are talking about checkpointing. Now what happens in checkpointing? Your secondary name node will talk to name node. So secondary name node comes in action. By default, the checkpointing is every 1 hour. However, this is customizable, right? Because you don't want to have checkpointing happening every 1 hour. That is a longer duration. You would like to have checkpointing happening more frequently. It might be like 10 minutes or might be like 20 minutes. So the default time is 1 hour. Now when secondary name node contacts name node, the first thing which will happen is you would have a new edits in progress immediately created. Now let's assume that this is edits in progress 3, which basically means that from 10:05, any change which happens on SDFS, whether you create a directory, you create a file, you delete a file, you move the file, or any other operation you do in SDFS, the changes will be recorded in edits in progress 03. Now what happened to the previous edits in progress? So checkpointing basically means that now the changes which were recorded in edits in progress will be merged to the existing FS image. So you would have basically a new FS image as of 10:03, which is a result of merging the changes from edits in progress to the existing FS image. So we have the initial file system image, and now we have a new file system image, which is with all the changes that happened between 10 to 10:05. So this should be 10:05, and all the changes which were basically merged are also you will see the static edits in your metadata path, and you would see them as edits like this, the static edits which were flushed from edits in progress to be merged and to create a new FS image. So we have secondary name node which is doing this at repeated intervals, either default 1 hour or based on the time setting. It contacts name node, it does the merging of changes in edits in progress to the existing file system image. It will create a new file system image. So you will always see the new file system image number, the last static edits would be pretty much same, and then you have edits in progress which will have the next number. So this checkpointing keeps happening, and not only that, secondary name node which is supposed to keep a copy of metadata will also have these static edits and edits in progress getting stored. Secondary name node will never have edits in progress. So secondary name node will have a copy of FS image and the edits, and this is why we say that secondary name node has a metadata backup. So in case your name node crashes, you would always use the copy of secondary name node's metadata to bring up a name node. However, you would only be able to bring your name node up to the last consistent FS image. So whatever changes were recorded in edits in progress and which were not merged to FS image will be lost in case name node fails and you are using secondary name node's copy of metadata. So this is how the checkpointing happens. Always remember, secondary name node regularly contacts name node based on the time interval set, It creates a new edits in progress, it merges the changes and edits in progress with the file system image, creates a new FS image, and it keeps a copy of the latest FS image and edits with itself. So this is what I mean when I talk about secondary name node doing the checkpointing, having a copy of metadata in its disk, basically making it possible to recover name node or to bring up a new name node if there is a name node failure scenario. Now, in a case of high availability, which we will learn later, you would have two name nodes, one is active and one is standby, wherein standby would be doing something what secondary name node does. We will not be allowed to use a secondary name node in a highly available cluster. So this is how overall how it looks. So you basically have name node, which is aware of blocks which are getting stored. Your client, which has to read or write data to the cluster, will always go via name node, and we know that name node has its metadata in RAM and metadata in disk, which is basically responsible for your complete cluster. So a simple question here: if a client wants to read data and it contacts name node will check in its metadata to give information to the client. The question is, which metadata will name node refer to? Will it refer to the metadata in RAM or will it refer to the metadata in disk? Think about it. So the answer is name node will refer to its metadata in RAM, and that's how it will respond to the client saying which data nodes are available and which data nodes have the blocks where the data resides and can be read from. So this is how overall all these components work together for your SDFS to be functional, for your Hadoop cluster to be accessible, to store huge amount of data, and also for your further processing requirements. Now in a rack-aware cluster, as I said, now this is a overall topology which shows up that your nodes might be placed in different racks. Now obviously in a particular organization you would not want to have all the racks connected to one switch, and that's why you would have top of rack switch which would be existing on every rack, and that would be connected to the core switch, which basically makes sure that a switch failure will not make a complete rack or will not make all the racks unavailable. Now before we get into read and write mechanism, as I mentioned about checkpointing, take it as a task. You can always do a Google and try to check what are the properties which are set for secondary name node to have a different checkpointing period. Take this as a task. You can look for SDFS default XML file in Google and search for the property which will then be set to make sure that your secondary name node does the checkpointing at a preferred time interval. Now I would also like to share one good link which explains about metadata, and that is your, let's look for this one, which is a blog link, but it basically explains the metadata and more details about it, which talks about what is getting stored in the name node's disk and what are these different things, what explains about your metadata. You need not get into journal node details as of now. You can just refer to the name node and data node details. Journal node and all that becomes important when we learn about high availability, but this is a very good link and I would recommend everyone to look into this. Now we will also learn on SDFS read and write mechanism. Now we know read and write are parallel activities. Replication is a sequential process. Always remember, replication of blocks cannot happen in parallel. So you would have a block being written and its replicas are created sequentially. Parallel, you would have multiple blocks being written and each block would have its replicas getting created across the data nodes. But remember, read and write is a parallel activity, replication is a sequential activity. Now to understand about your read mechanism, let's look at this where we will understand what happens when a client or an API or an application would want to read data and what happens when it tries to write data to the underlying data nodes. Now to understand read mechanism, we already have discussed that in case of read mechanism, it is basically name node which is playing a very, very important role. So to understand SDFS read mechanism, we already know that our data is getting stored in the underlying data nodes. We would always have a edge or a client node which would be used by users to connect to the cluster, and then basically you have your other processes, mainly your master process, that is your name node, right? So when we talk about your SDFS client, how does it do the reading? Now whenever a file has to be read, now that would be by a command from the command line from the client machine, or might be by an application which is trying to read, or you might have a GUI interface such as Hue which would be used to read data from SDFS. So what happens is when a client wants to read some data, or you can say when the read operations begin, the client will use an internal open method. Now we know that Hadoop framework has been coded in Java, right? So there are internally a lot of classes which are being used or methods which are being used. So the client uses the open method on the object. Now in our case it is the file which is on SDFS, and this open method is basically initiating a read request to the distributed file system. Now this distributed file system cannot answer this without consulting the name node, and we discussed that name node stores metadata in its RAM and its disk, wherein metadata in RAM is all about what are the files are related to which blocks, the blocks are sitting on which data nodes, and what are the file permissions. So once this open method is started and it initiates a read request, distributed file system will consult the name node to get the block locations of the file. Name node will look into its metadata in RAM and returns the sorted address of data nodes that hold the blocks. Now that's what name node is doing, and name node would always prefer the nearest data node. So out of all the data nodes, name node will give a sorted address of data nodes that are holding the blocks, wherein it will prefer to use the nearest data node. Now distributed file system, what it does is it returns an input stream called FS data input stream, and this FS data input stream, you can again consider this like a class which supports file seeks. Then the client or the requester which is trying to read the file will call a read method, and this read method will be on DFS input stream, that is a wrapper for this FS data input stream. So DFS input stream holds information of block locations for few blocks of the file. Now it can reach to those files, it can read that data from the closest data node that has the first block. Right now we know that there are replicas placed across the data nodes, and one of the replica has to be read for this read request. Now internally what is happening? Internally there is a block reader that gets initialized on data node using what kind of information, such as block ID or data start offset or client name, and what is the data to be read. Now data is streamed from data node and sent to the client in the form of packets. This data is copied in the input cache provided by the client. So there is an input cache which client has, and basically this data is copied into that cache. Then client reads data and performs a checksum, or you can say validation, right? And it also updates the client cache. Now this read method is called and repeated on the input stream till the end of the block. So this keeps happening in a repetitive way. Later this DFS input stream, which is a wrapper for this FS data input stream, will basically close the connection to the data node. Now once the client has finished reading the file, the close method will come into existence. So the close method is called to close the connection. So what we see is for a particular file, the blocks can be read in parallel. Okay, so as I said, read is a parallel mechanism. So you can have for a file multiple blocks which can be read, and this is the whole benefit of having a distributed file system. That in a distributed file system, rather than you reading from one central storage at a time, you would read multiple blocks from multiple machines at the same time, and this is what makes reading faster in a parallel fashion. So this is how it looks, right? So basically we have the client requesting the information to read block A and B. Name node is giving the information of location of those blocks. Then the client, now internally we can talk about the network details that it goes via the core switch, which is then connected to top of rack switches, and our nodes are placed in different racks, right? So this client will then try to read the data from the data nodes, and whichever is the nearest one. And finally, once the read is done, the data comes to the client cache, and basically once the read is done, client will have this close method initiated, which will close the connection. This is how your read is happening in a parallel fashion across multiple machines. Now, when we talk about write mechanism, similar activity. So write is also a parallel activity. Now we know that write activity in SDFS can only happen when name node confirms the availability of data nodes. And how does name node confirm that? It already has this metadata in its RAM, right? So data nodes are sending heartbeat to name node every 3 seconds, and based on that, name node is already building a metadata in its RAM, which it knows. Now, when a client wants to read the data, so unlike your write, unlike your read, where we were saying there was an open method, right? So here there will be a create method. So the client is placing a request to the distributed file system that I would want to write such files, and that is done by a create method. And for that to happen, distributed file system is again consulting name node, asking which data nodes are available. Now, once name node has responded back, right? So in case of read, we were talking about FS data input stream. Here we are talking about FS data output stream. And to this, again, you will have a DFS output stream, which will be the wrapper. So once your name node has responded back with the data nodes which are available, again, a sorted address and giving preference of which data nodes are nearby, your client basically will want to write data to the data nodes. Now we know that a file based on its size will be split into blocks, and it will be randomly distributed on the data nodes, right? So then your client, using this information, will then take the data or the file which is split by the framework into blocks, and those blocks will be written on the underlying data nodes. And again, for a particular file, your blocks can be written in parallel across multiple machines, and that's why I said write is also a parallel activity. But then how do we say replication is a sequential activity? So basically, when a particular data node receives a block, it internally triggers an event or an alert to another data node and informs to get ready so that there can be a replica written on the other data node. Now this process will continue, and each data node will inform the next data node to have a copy written, and that's why we call replication is a sequential activity, or you can consider this as a pipeline write. You can imagine this as 3 buckets which are connected with pipes at the bottom, and you're filling in water in one of the bucket. But then the water getting filled into the second bucket will not wait for the first bucket to be completely filled. So as the data starts coming into first data node, it would have already triggered an event to other data node, and second data node would have triggered an event to third data node. We are assuming here replication is 3, and then replication will happen sequentially. Now this also tells us that our data nodes which are sending block reports every 10 seconds to the name node are updating their information of what blocks are already successfully written, which basically means that you can read up to the last successfully written block. Always remember this. So while a block is written and replicated, other blocks of the same file or a different file are also being written on the underlying data node. So that's why it makes write mechanism also a parallel mechanism. You can write huge amount of data across your cluster in a parallel fashion, which makes your writes faster. Now whether your cluster is good for writes or whether your cluster is good for read, that may depend on the bandwidth which is between the data nodes, or what is the hardware, or what is the disk size, right? But then always remember your read and write are parallel mechanisms, and your replication is a sequential activity. So this is how it happens, and basically once the data is written, an acknowledgement is given back to FS data output stream indirectly, then to client, and client knows the write was successfully done. If we look at the flow, this is how a write mechanism looks like, where we talk about your client or an external machine which has access to write data to the cluster, consulting name node giving the responses of the data nodes being available, and then the flow of data happening from the client via the top of rack switch to the data nodes where the data will be actually stored. Now this is how your read and write happens, and basically as the data is written, data nodes are also giving an update to the name node. Now there might be situations then when the write is happening, there might be some data nodes which would have gone down, but that does not stop the write activity. It might make my blocks under replicated. That is, the blocks had to be written down, they had to be replicated, and due to some reason there were not enough data nodes available. At this point of time, I can ask you one simple question. In a cluster of 3 data nodes, let's imagine a cluster with 3 data nodes. What is the replication one can set, and what is the replication one can achieve? Think about it. In a cluster of 3 data nodes, what is the replication one can set, and what is the replication one can achieve? So what are the answers? Replication can be set to any number. It can be more than the available data nodes. But can we achieve that? We cannot. So the first rule of replication is a node will never have identical blocks sitting on itself. That means that for your cluster to have a replication consistency, to achieve a replication of 3, it will minimum need 3 data nodes. You could have more, but then if you have less number of data nodes, you cannot achieve the replication which has been set. So we can conclude this by saying that the replication which can be achieved can be maximum or equal to the number of data nodes available. You cannot go beyond that. And if your nodes are placed in racks, as I explained earlier, then in that case, the rack awareness rule also applies, where your replicas will be placed in such a way that in a rack, you will never have all the 3 replicas. Now, this is how your read and write mechanism happens, and replication happens in a cluster. Now that we have understood about read-write mechanism, we have understood about SDFS internals, we have understood about SDFS architecture, let's also talk about the second main component, or you can say layer of Hadoop framework, and that's your yarn. Now, yarn stands for yet another resource negotiator, and we'll see how that works. So as I mentioned earlier, in a Hadoop framework, you mainly have 2 layers. One is your storage layer, which is nothing but your disks, or you can say SDFS, which is supported by disks from multiple machines or multiple nodes. And then you have the processing layer, which is yarn, which is mainly for processing. So your processing layer would consist of your CPU cores and RAM. And we are talking about CPU cores and RAM from multiple machines. So what is yarn doing here? So if we assume that we have huge amount of data getting stored in a Hadoop cluster, then the benefit would only be if you can process that data. If you cannot process huge amount of data using multiple machines, then what's the benefit of cluster? It would just become a storage layer. Yarn takes care of that. Now let's see what is yarn and how it works. So if we look at the 3 main components or layers, you could say SDFS is the storage layer, yarn is the processing layer, which manages resource allocation, and then you have MapReduce or Hive or Spark and many other processing frameworks. Although MapReduce is one of the oldest and the most mature, and we'll learn more about that later. Let's learn what yarn does. So if we talk about a cluster, we are talking about multiple nodes connected together, multiple nodes which are offering CPU and RAM for processing, and then somebody has to manage those resources, such as memory usage, or what's the network bandwidth, or basically the disk IO or the CPU cores for the processing, and this is managed by yarn. Now in case of SDFS, as a storage layer, we had a master, that is one single name node, and you have multiple data nodes, right? Now in case of high availability, which again we can learn later, in case of high availability, you can have multiple masters, that is 2 name nodes, one as active and one as standby, and then you would have your data nodes. Similarly, in Yarn also, we can have a high availability setup where you would have 2 resource managers, one as active, one as standby. But then let's talk about high availability at a later stage. Let's understand the Yarn architecture and how it works. So here if you see, again we have client on the left hand side, which would have either the application or the command or basically an API running, which would be submitting the job request. In case of Yarn, we have the master of this processing layer, which is called resource manager. You have slaves, which are node managers, which are running across the machines. And if we talk about node managers, they will always be co-located with data nodes. The whole concept of Hadoop is about locality reference. The whole concept of Hadoop is that you don't move data from one place to other place for processing, but you move the processing logic to the machines where the data is stored. So when this processing logic lands on a particular machine, somebody has to take care of processing, and that is your node manager. So node managers are the slaves which will be running on the same machines wherever data nodes are running. We know data nodes are responsible to store the blocks, and node managers will be responsible to basically take care of processing on the nodes wherever the relevant data is. Now we also see something called as app master here, and that is a temporary process or a temporary daemon which was introduced with Yarn. So earlier in Hadoop version 1, instead of resource manager, we had a job tracker which was one single master, and instead of slaves such as node manager, we had task trackers. But the problem in Hadoop version 1 was that you had only one master, which is job tracker. There was no possibility of high availability. There was no possibility of app master. So basically, if your job tracker, which is doing job scheduling and resource management both, goes down, you cannot do any more processing. In case of Yarn, with resource manager, with node manager, and this app master, there is a possibility that even if your master, that is resource manager, crashes after the application was submitted, the application will still continue to run. Now we have some concepts of container here. We'll also see later when we learn about other aspects how these containers are allocated. But at this level, you can understand Yarn is taking care of this, and that is one of the reasons Yarn can support different kind of processing workloads. So it's not just MapReduce. So in Hadoop version 1, the only kind of processing which could be done was MapReduce or processing based on MapReduce. But with Yarn, you can do graph kind of processing, you can do massive parallel processing, you can do other kind of processing using this Yarn processing framework. So resource manager basically manages the resource allocation in the cluster. Now what does node manager do? Node manager also contributes and does some work here. When we talk about resource manager, it basically has 2 main components. One is your scheduler and one is your applications manager. So at a high level, I could say that resource manager is the master which is managing the resources. Resource manager is the one which is tracking the resources from multiple node managers. So we understand that every machine has CPU cores and RAM. So node managers, being the slaves, are sending heartbeat about their availability to resource manager, and they are also sending information of how much or how many resources they have. What is resource manager doing? It is tracking them. It knows in total how many resources are available in the cluster and which node manager is contributing what. Now that obviously depends on our configuration. Just a thought here. Say every node has 100 GB of RAM and every node has around 50 cores. Now let's say that every node has 100 GB RAM and 50 cores. So if I look at 3 nodes, then totally I have 300 GB RAM and 150 cores. But can I say that my total processing capacity is 300 GB RAM and 150 cores? That would be wrong, because you cannot allocate all the memory, all the cores only to one process which is node manager. There might be many other processes running. So in a cluster, other than your SDFS and Yarn, you would have other services like Hive or Impala or Scoop or HBase or Zookeeper or Kafka. Now for those services, you would have roles or processes running across the nodes. So in that case, we cannot say all the 100 GB which was available on a particular node would be allocated to node manager. In fact, the best strategy would be to consider all the services which are running, to consider the Cloudera-based services or Ambari-based services which are running, to consider overhead for each machine, and then decide on what amount of resources can be allocated per node manager. So if I say 100 GB RAM and 50 GB cores on every node, then some portion of it might be 60 GB RAM and might be 25 cores would be allocated per node to node manager. So in total, I would say that if I'm saying 60 GB RAM allocated to every node manager, then I'm saying 180 GB as my total processing memory. And if I say 25 cores, then I would say 75 cores across 3 nodes. So node manager, which has some resources allocated to itself, is giving that information to resource manager, saying these are the resources which I have. What resource manager does, it is basically keeping a track of it. Now, when we say resource manager, it's the master. So technically speaking, it is not just resource manager which is doing it, but internally it has other components which help it do or help it in doing these things. So you have a scheduler component and you have an applications manager. So what does scheduler do? Now, scheduler is not going to monitor the resources. It just allocates resources to various running applications. So in a cluster, you can imagine in a real-time environment, you might have multiple teams, say a development, production, and a testing team, or you would have different businesses which might be using the same cluster. And it would always be that one business or one team would have a priority over others. Now, then how does the resource segregation happen? It would always be a business team which would say, my applications are more critical and I would need more resources in comparison to other business units. So there has to be someone who allocates resources to various running applications which might be coming from various different teams or various different business units. And for allocating these resources, there has to be some kind of scheduling done. Well, there is a mechanism of queuing. So there could be queues created like a production, development, and test queue, or basically a business unit 1, business unit 2, and business unit 3. And then in these queues, you could have specific business departments jobs landing in. And these queues would be allocated a minimum, maximum kind of resources. There could be some kind of sharing which can be enabled. So scheduler takes care of all that. It does not monitor or track the status of applications. Its only work is to basically allocate resources and make sure that those resources are available for the applications. Now, what does the applications manager does? It accepts the job submissions. So whenever there is a job submission, whenever there is an application which needs to be run, that request is handled by applications manager. And in case there is a failure of application, probably there were not enough resources, probably the node failed, probably there was a connectivity issue, probably a machine was overloaded. In that case, it is the work of applications manager which monitors and restarts the application master. Now, what is application master doing here? So as I mentioned, your node manager is a tracker that tracks the jobs running. It monitors each container's resource utilization. So here we are talking about 2 terms. One is app master, one is container. So what is an application master? How does it work? What is a container? So to begin with, let's look into this. So when you talk about resource manager, now we know resource manager and its components are internally tracking the resources from node manager. So whenever a application would want to run, obviously the client or an API would have contacted the name node. Name node would have given the information of the blocks which are residing on the data nodes, from where the data can be fetched, where the data can be processed. Now, whenever an application comes to the client, so your application would first talk to the resource manager. Now, your resource manager basically has got a request, and who has got a request in resource manager? Is the applications manager. Now, as soon as the application comes to resource manager, based on the internal calculators which Yarn has, based on the request of application, and based on resource manager's knowledge of what resources are already available, the resource manager would basically make a request multiple node managers. So it makes a request to multiple node managers depending on what data is stored on those nodes. And what request does it make? It makes a request of the amount of resources it needs. So it says, can you give me 2 GB RAM and 2 CPU cores? Can you give me 4 GB RAM and 4 CPU cores? Can you give me 10 GB RAM and 10 CPU cores? So this request of resources can be considered as a container. So your resource manager is basically making a request saying, I would like to have these many resources from you because you are on a machine which has relevant data, and I would like to process this amount of data on this node. Node manager, which is a slave which is aware of its resources, can accept or deny this. So resource node manager is the one which is basically approving or listening to this request and approving that yes, it can grant these resources. The resources which were requested by resource manager, basically your node manager is basically approving those resources. Now once node manager says yes, I can allocate those resources, I can give you this container, right? So container is a logical term. Instead of every time saying I would need so much CPU core, so much RAM, it would be easier to say resource manager is asking for a container which is of this and this size. And again, it depends on the configurations which are done in the cluster. So on every node at high level you would have this much amount of memory and RAM was allocated to node manager, and in that again you would have a smaller container size or a bigger container size. So a smaller container could be, okay, we are talking about 1 GB RAM and we are talking about 1 CPU core. The biggest container could be 3 GB RAM and 3 CPU cores. So out of total 100 GB RAM which was allocated to node manager, always remember 100 GB RAM which I'm pointing out is some portion of the memory which is available on that node. So 100 GB RAM and say 50 cores, virtual cores, out of that total which has been allocated to node manager, you could again have in configuration define what will be my smallest container, which is say 1 GB RAM and 1 CPU core, and a biggest container with 3 GB RAM and 3 CPU cores, and you can do the calculation. So if it is 100 GB and 50 V cores, so basically we could have 50 small containers running at a time, or we could have around, if I divide this, then I would say around 15 big containers running or 16 big containers running, which would be utilizing the CPU and RAM. So the sizing of the containers has to be very efficiently done, because in my first case when I said my smallest container is 1 GB RAM and 1 CPU core, that means I would have maximum 50 containers and 50 GB memory would not be used at all because there are no cores left. If you talk about 3 GB RAM and 3 CPU cores, then taking cores at the lower end, I could say might be 16 containers would be running. That means approximately 52 GB would not be used. So the sizing of the containers has to be done efficiently. But then once your node manager has guaranteed and said yes, I can give you the container what you want, that's when your resource manager will start a piece of code called application master. So an application master is started once the container request is granted by the node manager, and this application master is per application. So if I have 10 applications submitted to the yarn, then I would have 10 app masters running in parallel. And where would these app masters run? So this app master is a code, so it will run in one of the containers. In one of the containers you would have this app master running, and this app master is responsible for the execution of application. So basically the resource manager is saying I will only track the resources with the use of my components, but once I have negotiated the resources, once I've gotten approval of containers, I will give this whole task of getting the execution done to the app master. And this is what I meant, that in a yarn based framework, even if your master gets killed after the application was started, after app master was allocated, the responsibility, the application will continue to run. The only thing is it will not be able to communicate back if the application is completed. So app master is the one which will run in one of the containers, and it will use all the other containers from all other nodes to get the execution done. Now in any case, if a particular app master itself gets killed, say it was running on node 1 and node 1 crashed, now in that case it is the role of applications manager, which we discussed in resource manager's component, which will relaunch a new app master. But app master is the one which uses the containers, gets the execution done, and once all the execution is done, it will communicate back to resource manager. So it is the work of an app master to communicate back to resource manager that processing is done. So remember, application master plays a very important role here. Now node manager is approving the containers, resource manager is the one which is always negotiating the resources. So that also means that if a app master realizes that it needs more resources, it cannot directly talk to node manager, it cannot negotiate the resources, it can only use the resources which resource manager had got approved. So application master will always go back to resource manager asking for more containers. Resource manager is the one which will talk to node managers and basically get the containers. So your application master manages resources needed for individual applications. It internally also interacts with scheduler to acquire the resources based on the policies which are set, based on what kind of scheduler you're using, and then it interacts with node manager to execute the application task within the container. Now your application could be a Spark application which would be running within the container, right? And in the case of Spark, which we can learn later, is there would be an executed process which takes care of your Spark application, which is broken down into tasks, and those tasks will run within the container. In case of MapReduce, your application will be broken down in tasks, and those tasks will be running within this container. Who is getting the execution done? It's the app master. Who is negotiating the resources? Resource manager. Who is approving the resources? It's node manager. What are these resources? Containers. Now that's what we mean by yarn as a framework. So container is just a logical term for collection of resources like RAM, CPU, network bandwidth, and so on. And it is always allocated based on what yarn has calculated for resources. So there is a very good link about yarn and how it works, and you could look for yarn untangling. And this is a series of 4 blogs which I would recommend everyone to read through, which talks about how yarn works. So basically it talks about how resources are allocated, what is your master and slave process, what are your resources, and basically once the container is allocated, what happens within the container, and it talks about your application master and the components. And if you talk about MapReduce, which we will learn in later sessions, it also shows that if it was your map task or a reduce task, that would be running within the container. So this is a very good link, and you could always look into the part 2 of this, which basically talks about resource allocation, which talks about how resource allocation is done, what would be the properties for container sizing, and basically how it is done, which is about right resource allocation. So please look into this blog. This is one of the good blogs which talks about yarn and the processing layer. Now after yarn, we will then start learning about the processing framework and the programming model, that is MapReduce, which basically allows to process the data using yarn on a Hadoop cluster. We will learn on Hadoop MapReduce, one of the oldest and most mature processing frameworks, which is used for processing huge amount of data. Now we have learned about some basics on Hadoop MapReduce, and let's also spend some time in understanding what is MapReduce, how it works, and how it helps us in processing huge amount of data. So MapReduce is a framework, or you could say MapReduce is a programming model which is not restricted to be written only in Java. That could be written in Python, that could be written using other programming languages also. So it is a programming model, it's a framework that performs distributed and parallel processing of large volumes of data. Now this basically depends on 2 main phases. So you have a mapping phase and you have a reducing phase. Now what we know is that in a Hadoop cluster, you would have multiple machines, which would be your slave machines where actually the data is stored. On the same slave machines, you would also have processing slaves, which would be running to take care of processing the data locally. So you would have your data getting stored in the form of blocks, and the underlying data nodes on the disks, and on the same machines you would also have node manager, which is the processing slave, which would take care of processing the data which is getting stored on the nodes. Now your data could be read from these data nodes, or we could be processing the data to achieve some results. So you have two main phases here. Now if you look at the diagram here, mapping phase is mainly responsible to run a particular function or a particular task on your one or multiple splits or multiple inputs as you want to process, and finally delivering a key value pair. Reducing is something which receives this key value pairs from map jobs. So reducing depends on the input or depends on the output of MapReduce, receives the key value pairs. Internally there would also be some shuffling and sorting involved. Now there are many other phases such as partitioner, such as combiner, which basically help what reducer is supposed to do, and reducer or your reducing phase basically aggregates the key value pairs into smaller sets, thus giving you the result. So you would have your input data, which would then be handled by your mapper function. Now mapper function is given by the developer, and mapper function, as I said, is supposed to run a function on every input split, and that I could call as map tasks. So you could have one or multiple map tasks depending on the size of your file, depending on the configuration what you have set up, and based on these map tasks you would have intermittent data which would be created. Now this intermittent data then has to be sorted and shuffled. Now when we have our input data, our map task will basically work on your input data which is internally split depending on the size of the file, and then that data has to be sorted and shuffled. The intermittent data which is generated by map has to be sorted and shuffled, finally forwarding into the reducing phase where you have a reducer function responsible to do the aggregation, and then you would have your output data. So this is how it would look when we talk about MapReduce job execution. You would have your data stored in SDFS. Now you could have your data being pulled out from SDFS or any of other Hadoop components which can be used for data storage. This data would then have to be read. So somebody has to specify the input format, and who would do that? It would be the developer. So there are various input formats, text format being the default. Now you have key value format, you have binary format, and I'll share some links where you can read more about these input formats. So input format is specified, and based on the input format, based on the size of the file, your file is split into multiple chunks. Now by default the chunk size is equal to your block size, but then that is also customizable. So your file, if you're processing one file and if it is bigger than the block size, say the default block size is 128 MB, so if the file is broken down into blocks, then you would have multiple splits, and the number of splits would be equal to the number of blocks. Now these are the input splits which need to be worked upon. So you would internally have a record reader which reads the data from these input splits, and it basically forwards this information to the mapper function. So this is where our mapping phase starts, and in a MapReduce job execution, once and only if mapping phase completes, reducing would start. So in mapping phase you would have a mapper function again provided by the developer, and this mapper function would have internal code which would then be used to work on these chunks. So we have the mapping phase where mapper function is doing the map tasks, and the number of map tasks would depend on the number of splits which need to be processed. Now what is this mapper working upon? It will work on the data, and then basically what it does is it transforms, or you can say it processes the data. It breaks the records in every chunk into a list of data elements, and this data elements is nothing but a list of key value pairs. Now there could be a combiner phase which is acting like a mini reducer. So reducer, which is part of your reducing phase, would be responsible to aggregate the data, but then before the data reaches the reducer, it can also pass through combiner provided developer has coded in that way, and combiner basically does kind of mini reducing. Now your combiner would work on this intermediate data which was created by map tasks. So the data which was generated as an output from map task is not the final output, it is an intermediate key value pair. Combiner would basically work on these, and then it would also be using partitioner. Now partitioner is an internal phase, so partitioner, depending on these key value pairs, will decide how many reducers or how many reduce tasks would be required to aggregate this data. Now this depends on the key value pairs, it depends on the type of keys. It also depends if you have hard-coded configuration property which says that for my every job I would want to use specific number of reduce tasks. So either it would be depending on the configuration property, or it would be depending on the partitioner which decides on how many reduce tasks would be required to process your data. So your combiner and partitioner work on this intermediate key value pair. There would be sorting and shuffling, as I mentioned earlier. So you have a lot of data, you would have a lot of keys and values, and when we talk about aggregation, we talk about some kind of similarity which these keys have. So there has to be sorting and shuffling. Now all this is happening in the staging area, and this is one of the reasons MapReduce, although being oldest and the most mature, is slow, because all the output generated from map task is written to SDFS in the staging area, or you could say an intermediate layer from where it is picked up for further processing. So sorting and shuffling is done, and then finally your reducing phase gets its input, where you would have reducer function again provided by the developer, which takes care of reduce tasks and giving you the output. Now we know that input can be accessed from SDFS and output can be accessed from SDFS, but technically speaking you could say that data is stored on a data node, it is processed on the same data node, and then you would have the output of that stored internally on the same node. But actually we know that we don't access the data directly from data nodes, we access it through SDFS. So based on the output format which has been decided, the output is then stored in SDFS. Now this is how your MapReduce execution works. So big data comes in various formats, and data can be stored in different servers. So we know about this. You can have different formats like Avro or Parquet or text or binary in compressed, and many other formats which are available. Now whichever way the data is stored, MapReduce is capable to work. However, remember, if the data is compressed, then we would have to look into the compression mechanisms to see if compression mechanisms support splittability. Okay, now your big data comes in various formats, and then this data is split, obviously depending on the size of data, depending on how many available data nodes you have, and this split is then worked upon by the mapping phase, which will basically break the records in each chunk of data which it is working on to give you a list of data elements. So if we take an example of a word count, the classic example of MapReduce, and if I'm subjecting a file to be processed where I would want to count the words, then each line in this file, now again I'm assuming here the default format is text. Now there can be other formats also. If the format is text, if it is a file which you want to process, then each record, that is each line is considered as a record, will be broken down into individual key value pairs. And this is how it would look, where I would have a word and then a value to that word, number 1 for example, which would be appended, which gives me a key value pair. Then we would have some kind of sorting and shuffling where similar keys are brought in and kept together so that it becomes easier for further phases. And then you have your reducing, which will then look into keys and values, see if the keys are repetitive, and then basically aggregate the values to give me a total word count. Now we can discuss on yarn, which takes care of processing requirement, but then here when we spoke about MapReduce, we are talking about MapReduce, which basically is used to process use data. Now we can take an example of word count, the standard word count example, which can be submitted on a running cluster, whether that is Apache, whether that is Cloudera or Hortonworks or any other distribution, and we can take a classic example of word count, which allows us to process the data. To have an example of MapReduce and the word count, let's look at a demo. To test our word count example, which uses MapReduce programming model, what we would need is one or multiple input files which should be existing on the cluster. We would need a path on SDFS where we would want to place the output. We would need the jar file which has classes packaged as jar, and especially we would need the word count class, and then we can run this on the cluster. Now in an Apache cluster we can already find the MapReduce existing, the word count example existing in the jar. However, the other option is you building your own word count, and I'll show you that. So here we can go to the cluster. Now it's a 2-node cluster. However, I've not started my second data node and second node manager so that I don't have any resource constraints, and I can look into this cluster where earlier also I have run some applications. So we know that in an Apache cluster or in a Cloudera cluster you have the yarn UI, and you also have the name node UI which can be used to look into the cluster, to browse your files, and basically to look at the status of your cluster. So this should be your name node UI, and then you have the yarn UI which can be used to monitor your applications. Now as I said, there can be two ways in which you can submit a MapReduce. One is using some inbuilt jars. Now here in an Apache cluster, in my user local directory, I have the Hadoop directory which we can see in user local, and within my Hadoop directory I have a directory called share. So let's look into that. So let's go to user local, and here we have share. In that we have Hadoop. In this Hadoop we have MapReduce, yarn, tools, other subdirectories. Let's go into MapReduce, which has some sample jar files, and we can take the example that is Hadoop MapReduce examples. I can say Hadoop, or to run a jar we can just type in Hadoop. Now that shows me that I have an option called jar, so I can say Hadoop jar, and then I can give this path which is share Hadoop MapReduce examples, and then I can see what classes are available. So these are different classes or programs which are available, which are by default existing in Apache cluster under share Hadoop MapReduce. You could also find a similar jar file in Cloudera by looking in opt Cloudera parcels cdh/lib/Hadoop-MapReduce directory. Now we would want to run this, but then as I said, we would want to run it on a particular file or a set of files, so we can see what exists on my SDFS. And in my SDFS I have various directories, and those directories have multiple files. So either I can run a word count which uses MapReduce programming model on a particular directory or on a particular file. So as I mentioned, if you have a file which is smaller than 128 MB, it would basically be using one block, which basically means it would be one split on which your mapping would work on. Now we would be interested in doing a word count on this particular file, and we can see what is the content of this file by looking into the file which is existing here in my local machine, and this is the file, so I can see what is the content. So there are some lines here. We could always do a simple word count using Linux utilities also like this, which says show me the number of lines in this file or show me the number of words in this file, but then it would not be possible if this was a terabytes file which is stored across multiple machines to do something like this. So that's why we would use MapReduce, and I will demonstrate an example of word count here. Now to do a word count, what we need is Hadoop jar command. We need to pass the path wherever we have our jar file. Now we are using an inbuilt provided jar file. We could also be writing our own code using an IDE like Eclipse, and you could write your own word count program. I'll explain this later, which can then be packaged as a jar file. Now here we see this is a sample word count program where we are importing some packages. We are specifying the driver configuration, which knows what is your mapper class, what is your reducer class, what is the input and output format you would want to specify, and if you want to specify a combiner class. And then if we further go down in the code, this shows me what my mapper function would do. That is, one or multiple map tasks would be doing this on my chunk of data splits, and then you have reducer which would be doing the aggregation. So we can write our own code like this in IDE, package it as jar, transfer it to the node of the cluster or edge node of the cluster, and then submit it. Here we will use an inbuilt example, so I'll say user local Hadoop share Hadoop MapReduce examples word count. Now here I would want to work on a file, so I'll take this directory and I can take my file which is existing there, which I just now showed, has around 36 lines and multiple words, and we would want to do this on one single file which is smaller than 128 MB, which accounts to one block, and that basically means one split which will have to be worked on by first your mapping phase. Now we also need a output location where our MapReduce can write its output, so let's give it a name, and this directory will automatically be created by Hadoop. Now with your word count, before you give your input and output, you could also be passing in different arguments to give properties to control what would be your output format. Do you want the output to be compressed? Do you want to apply some other property? Do you want to specify how many map and reduce tasks you want your job to run? Do you want to specify how much memory your every map task and reduce task should use? So either those properties could be hard-coded in Hadoop config files by your admin, or we could be specifying on the command line. So let's run this job, which is a sample word count on a single file, which will then also create an output. So the first thing it does is it contacts the resource manager, because we are intending to run our application on yarn. Now once it connects to resource manager, then it needs to get some resources, and who takes care of that? It is your yarn. Now until and unless your yarn successfully can allocate resources for your application, it will remain in undefined status, and then it will move into running status, and you would see this progress bar moving. Now we have not started a history server, but then we can look or browse for information about our application on the UI, and once the application completes, you could look for detailed information provided you also had a history server. So I already see there is some progress happening on the application. I see the progress bar which shows sub movement, and if I look into my terminal, I see that it has gone into mapping phase now, and only once the mapping phase completes, it will proceed for reducing. Now internally there will be some sorting, shuffling, and combining which will be happening. So I see my application moving here. I can click on my application while it is running. I can see that it has an attempt ID. It tells on which node it is running. It also points me to the logs, and if I have the history server enabled, I can click on history and look for more information. Now let's go back to the terminal and let's see what happened here. So as I said, our file basically had around 36 lines, and as I said, each line is considered as a record. So you can also confirm that. It says map input records is 36. Now those records are broken down into individual words. So you have output records as 638, and if we totally see, my file did contain 638 words. Now our purpose of word count is basically to look at the file. So we had one input part to process, that was number of split is 1, which also relates to the number of map tasks, which is 1. Now number of reduce tasks being 1 is decided internally by the partitioner phase, or based on the configuration property which you would have set to decide how many reduce tasks would you need for every job. So here I have map task 1, reduce task 1. I also see my map creates 638 output records. Now that would be taken as an input by the combiner, which is like a mini reducer, and based on the words, based on the similarity, it already does some kind of aggregation but not the final output. It it gives 335 records, which become an input for reduce phase, and then your reduce will finally aggregate the data. If I look into my output file, I would totally have 335 lines or 335 words and count of those words. Now this also tells me how much garbage collection time was spent, CPU time, milliseconds was spent, and this can be used to compare your application performance. So my application has completed. If I go and look into the output, so I can basically say if this was my output directory, as we mentioned, then this would have a_success file, which shows that the MapReduce completed fine, and it also shows this part file. Now this part file depends on how many reduce tasks were run, and this will basically tell me the output created, which would be a word count of the records or the lines which were existing in my file, which we use for processing. So this is how I'm using an inbuilt MapReduce job, and I'm doing a word count on one single file, which is one single split, and getting a list of words and the count of those words. Now similarly, I could be running the same word count by just changing the output directory, and I could instead run it on a bigger amount of data that is on the complete directory. Now I could be giving properties here, so I could say -d mapreduce.job.reduces, and I could say I would want my job to use 3 reduce tasks. I don't want the partitioner to decide that, and I could be specifying properties. And you can be giving multiple properties, and if by any chance the property what you have specified is wrong in the convention what you have given, or if there is a spelling mistake, that property will be ignored. It will not affect your job run. So right now we have submitted the same word count to work on my directory, which has totally 10 files, that means 10 splits, to be worked upon by our MapReduce, which should first go into mapping phase and then it should go into reducing phase. So we can come back to the Yarn UI, we can do a refresh here, and which will basically show me if my application has already contacted Yarn, then it should show me my application listed here, and basically showing some more information about the resources it consumes, how many map and reduce tasks will run, and so on. So we can always look for output from the terminal. We can always be browsing the UI, which is a general way of doing by looking at the applications in a production environment, and you can be running your word count. To find out some more example on word count on MapReduce, I would suggest 2 links. So one is you can say developer MapReduce tutorial, and that's a very good link which explains about all mapping phase and all reducing phase, how your mapping works, how your reducing works, and it also gives you the sample code, which is the word count program, which we are right now running on our cluster from our Hadoop MapReduce example. So this is a very good link which I would suggest everyone to look into. You can always find different kind of data sets from internet, and there are various sites where you can get free data sets. Now let's see what is happening with my machine here, because I've given a bigger input. I've given a input which is basically multiple files. So if you see here, it is basically going for mapping phase where multiple map tasks would be running depending on the number of splits. So as I said, we had 10 splits, so basically there should be 10 map tasks should be running. We should also be able to see our application progress from the Yarn UI. If you have some problem here, maybe we can just clear off this cluster option from the address bar, because Yarn UI basically gives you more information from one centralized place rather than you knowing all the commands from command line to get your job output. So my resource manager is running on C1, and the default port it listens on is 8088, and basically we can try to bring up the UI. So it's slowly coming up, and probably my application will have already completed. So if you see here, it is in running status, my application, and if we go to the terminal, we can see that it has almost reached the end of mapping and then getting into reducing. Right now, you might have some map tasks which you have completed on some nodes, and if you have decided that you will use multiple reduce tasks, then you could also see some reduce tasks which have already started working on map output. Now the job has completed. We worked on totally 10 files, and basically we specified how many reduce tasks we need. So it has gone for 10 map tasks, that is based on 10 splits, and 3 reduce tasks which were used for our job, which basically means that if I look into my output directory, I would probably now see more than one part file, which says per reduce task you would have multiple part files. So my job used 3 reduce tasks because that's what I specified on my command line, and here we have an output which can be then looked upon from either your browser interface or from command line. And if basically I look at my Yarn UI, that should show me the application running. Now one more hint here, sometimes when your application gets stuck and it's not moving, you can click on the application and you have an option called kill application, which allows you to kill the application, and then you can decide to resubmit this. So this is how your MapReduce works. Now we will learn in detail about MapReduce in further sessions, but this is how you can try out a sample word count, which you can always find from internet. If you would want to copy paste it in your Eclipse, export it as jar and then run it, that's also possible. Or you could be using these inbuilt programs which are available in Hadoop MapReduce examples.jar file. Thank you and keep learning.
Hi there, if you like this video, subscribe to the Simple Learn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.